Okay, folks, let me show you how to do one of these problems. We've got a charge in the diagram, the highlighted diagram. We got a charge moving into the page and between two poles of two different magnets, a north pole and a south pole, and we need to find the magnetic force that acts on that charge in that field. And there's two things we're going to want to know about the force: the direction and the magnitude. So let's find the direction first using the right-hand rule and this little diagram, or this little coordinate axes that I have to the right. I'm going to put the positive charge at the origin because that's the simplest way to do this, and the charge is moving into the page on the negative z axis. The magnetic field should go from the north pole to the south pole like this. So the magnetic field should be to the left. Remember, magnetic fields go away from north poles and towards the south pole. So the magnetic field is to the left on that negative x axis, and we need to find the direction of the force. And there's only really two possibilities. It's either going to be up or down. But which is it? Well, the reason it can either be up or down and not anything else is because it has to be perpendicular to the velocity and the magnetic field, V and B. So the only way that can happen is if it's on an entirely different axis. It has to be on the y-axis. It has to be up or down. If it was on the x-axis, it'd be parallel to B, and there would be no force. And if the force was on the v-axis, on the z-axis, it would be parallel to V. So that can't happen either. So it's either got to be up or down. And if we use the right hand rule, I'm going to draw my little orange hand here. The thumb points in the direction of V if you use the palm method, and the fingers point to the left in the direction of B. So your hand, if that was your right hand, your palm would be facing up like this. So the force on this charge is up. That's the direction. Now let's find the magnitude. The magnitude depends on a few things. It depends on the charge quantity Q, the velocity V, the magnetic field strength at this point, which is 5 milliteslas, and it depends on the angle between V and B, theta. So the angle in this case is 90 degrees. They're perpendicular because they are on different axes. If they were on the same axis, like if both on the x or both on the y, then the angle between them would be 0, and there would be no force to speak of here. There wouldn't be a force. So we know they're 90 degrees because they're on two different axes, and that would be true if they were on any two different axes, because these three axes are defined to be perpendicular to each other. This will mean that the sine of theta will be 1. The sine of theta is 1. So let's get to calculating. The magnetic force will be the charge quantity, positive 5 picocoulombs, times the velocity, 100 meters per second, kilometers per second, times the magnetic field strength, 5 milliteslas, and the sine of 90 degrees. We need to convert these first before we multiply. So pico is times 10 to the negative 12th. Kilo is times 10 to the third. Milli is times 10 to the negative third, and the sine of 90 degrees is just 1. Make sure, if you're calculating the sine, like you forget what the sine of 90 degrees is, that you are putting your calculator in degrees. Use the arrows to go down and then go over and hit degrees before you do anything with the sine. Alright. So don't forget your parentheses. 5 times 10 to the negative 12th times 100 times 10 to the third times 5 times 10 to the negative third times the sine of 90, which that's just 1. We don't really have to put that there. We're just multiplying times 1, but that's how it would all look in the calculator, and that's what it should give us. The force on this charge is 2.5 times 10 to the negative 9th newtons, or 2.5 times 10 to the negative 9th stands for nano, so 2.5 nanonewtons of force acts on this charge in the upward direction. And that is how you deal with a problem like that. Thanks for watching.